let's proceed with the next talk, which is given by Aidan Perreault. So please.
Okay, so I'll be talking about joint work with Aditya, Bhaskara, Aidao, Chen, and Aravindan, Vijayaraghavan. So the talk will kind of roughly follow the plan laid out in the title. So first, I'll start by introducing what smooth analysis is, and then I'll talk about problems in obtaining these results for some unsupervised learning problems when you're dealing with high-dimensional data. And then I'll show you how you can resolve some of these problems using decoupling techniques. So first, smooth analysis tries to answer the question of why some algorithms perform well in practice, even though in the worst case, they could be intractable. So if we wanted to get worst case guarantees, we'd need the algorithm to perform well on the entire input space. So it would look something like this. And that's just not going to be the case for algorithms that we're looking at. So we'll need some sort of more nuanced analysis. One option might be to do an average case analysis, but there could be two problems with this, at least. One is that maybe the algorithm performs well on average, but there's still some region in which it performs badly, and you might not be able to avoid that region in practice. Another problem is in order to get these average case results, you actually need a distribution over the inputs, and you might not have that. So smooth analysis tries to kind of resolve problems with both of these scenarios, and aims to capture the situation where your algorithm has some bad input cases, but they're rare and they're isolated, so that if you look at any small neighborhood within the input space, most of the points are good for the algorithm. So to formalize this a little bit more, you start with an arbitrary input A, which could be worst case, and then you add a small random perturbation to get A tilde. You can think of this if A is a string, maybe you're flipping a couple bits, or if A is a vector, then you're adding a small Gaussian noise to it. And then the hope is that you can prove guarantees for your algorithm when you run it on this perturbed input A tilde that hold with high probability over the random perturbations that you add. And so the picture looks something like this. You start with an arbitrary point. You add a perturbation, so you get another point within a small neighborhood of the original one, and your hope is that most of those points in the neighborhood are good. And this has been used to get lots of interesting results. Possibly the first and most famous is that you can show an explanation for why the simplex algorithm performs well in practice, even though in the worst case it's NP-hard. And then there are lots of other applications as well. So now I'll specify it to the types of problems that we looked at. So we're looking at unsupervised learning in high dimensions, and a kind of prototypical example of this is the tensor decomposition problem. So the problem is you start with a tensor, which is just a multi-dimensional array of numbers, and the order L of the tensor is the dimension of this array. So here we have the third order tensor. And we want to write it as a sum of rank 1 tensors, where a rank 1 tensor is just an outer product of L vectors. So you get something like this. You start with a tensor, and you write it as a sum of rank 1 tensors. And you can think of this as a generalization of decomposing a matrix into rank 1 matrices using SVD or something. And we say the rank of a tensor is the minimum number of components you need in any decomposition. There are lots of reasons you might care about tensor decomposition. Maybe it's just useful to break your tensor up into simpler components that you can deal with one at a time. Another interesting fact is that tensor decompositions are actually unique as long as the order of your tensor is at least 3, which means that if you care about the specific parameters in the decomposition, you can actually recover those from tensor decomposition. And you can use this to, for example, learn the means of a mixture of Gaussians. Okay, so our problem is, given a tensor, we want to find a minimum rank decomposition. The bad news is that this is NP-hard if the rank of your tensor is larger than n or so. The good news, of course, is that smooth analysis can help. So Bhaskara, and Vijayaraghavan showed that if instead of dealing with a worst case tensor, you first add some small Gaussian noise to these input vectors, and then you tensor them together and add them up to get T. Then with high probability, you can find a decomposition even when the order of your tensor is up to n to the L-1/2. Okay, so tensor decomposition is an example of one of these more general unsupervised learning problems, and I'll kind of move towards that generalization now. So the intuition of why smooth analysis works is that the bad cases are rare and isolated, and specifically, in this case, the bad cases correspond to some sort of degenerate configuration of those input vectors AI. And specifically by degenerate, I mean that some matrix that you can construct from the AIs is singular. And there are lots of problems that fit this framework with a different matrix M. So for example, the matrix M for tensor decomposition has k columns, and each one of those k columns is just one of the components of the decomposition. For learning hidden Markov models, which I'll talk about later, you have a similar thing, except that the columns are determined by a tensor product that somehow corresponds to paths through the state space. And I'll give more details later. There's one slight abuse of notation I should mention. So I said that a tensor product is an L-dimensional array. Here, in order to view that as a column of a matrix, I'm just flattening it. So I'm stacking up all the coordinates into one long vector. So that's what this picture is showing. Now, in order to get smooth analysis results for these problems, it's not enough to just show that M is full rank, because the problem is that these algorithms depend polynomially on the condition number. So we need to be kind of robustly full rank in a sense. We need a polynomial upper bound on the condition number, which is the ratio of the largest singular value to the smallest. Upper bounding the largest singular value is usually not hard. You can use standard concentration results. The challenge comes when you want to give a lower bound for the smallest singular value. So that's what this talk will focus on. Even in a kind of classical random matrix theory setting where all of the entries of M are independent, it's still a non-trivial problem. But here we have the additional challenge that our matrix has lots of dependencies between all of its entries. So as one example, if we're dealing with the tensor decomposition case again, I'm just going to look at one column of our matrix M for now, which is a tensor product of L vectors. Here you have n coordinates per vector and L vectors, so you have n times L sources of randomness. On the other hand, you have n to the L coordinates, so you just don't have enough randomness to have independence, so you have to have lots of dependencies between all of the entries of your matrix. So that means that the general question we want to answer is if you have a matrix of this form, where the columns are given by some polynomials of your input vectors, when can we get good lower bounds on the smallest singular value? So this should hopefully resolve the main technical challenge in giving smooth analysis results in this type of setting. There's been some progress towards this goal, first of which is for this tensor decomposition problem. And that says if you have a matrix M with a specific structure where each of the columns is given by a tensor product of L independently perturbed vectors, then you can get these good bounds on the least singular value. And then some later works deal with differently structured M's that are somehow more challenging. So for example, Ma, Shi, and Server dealt with an M of this form, and there are two things to notice about why this is more difficult than the original case. So first, in the first bullet point, any input vector AI can only appear in one column. So all of the columns of your matrix M are independent. Whereas in the second case, it'll appear in multiple columns. It'll appear once for each different value of J. And the second problem is that in the second case, you have a fourth order tensor for each column, but you only have two input vectors. So you have even less randomness per column to work with. So this is an example of the two general challenges that we'll face with regards to this lack of independence when we're trying to get bounds on the least singular value for M. So one is dependencies within one column of M. So for example, if your column is A tensor twice or something, then the first coordinate of your vector A will appear across multiple entries of the column, and so those will all be dependent. And the second type is dependencies between columns. So if the same vector is an input to multiple columns, so for example here, A1 appears across two columns and A2 appears across two columns, then you'll also have dependencies between those columns. And I guess I should mention, the reason that these dependencies are a problem for us is that when all your vectors are independent, you can expect that they'll be roughly orthogonal so that the least singular value is large. But when you have dependencies, you don't know that for sure. So we have to find a way around this. So now I'll talk about two kind of classes of matrices M where we can resolve these problems, and then I'll give some applications to unsupervised learning problems. So our general goal was to give a characterization of when we can get this polynomial lower bound on the least singular value. We can do it in two general cases. So the first one is where we have a matrix M where each column is some polynomial of one input vector. So in this case, we'll have to deal with the first type of dependence where you have the same perturbed input that appears across multiple columns. The second case is where each column of M is an arbitrary tensor product of some input vectors. And here, one vector could appear multiple times within one column, or it could appear across multiple columns, so we'll have to deal with both types of problematic dependencies. And you can think of both of these as kind of a generalization of the original tensor decomposition result in two different directions. So in the first case, we're generalizing the type of polynomial that each column of M can be. And in the second case, we're generalizing the kind of arrangement of the tensor products. From instead of requiring that each vector is independently perturbed, now we can have repeats. And once I give those technical results, I'll give 3 applications to unsupervised learning problems. I'll talk about robust subspace recovery, hidden Markov models, and higher order tensor decomposition, a new algorithm. So in our first result, here's the setup. So we start with the same Gaussian perturbed vectors. We get k vectors in Rn, and then we add a Gaussian perturbation of variance rho squared. Next, I'll define the polynomials that give our matrix. So each fi is going to be an order L homogeneous, or degree L, sorry, homogeneous polynomial. You can notice that inside X tensor L, if you look at all the coordinates, you'll find all of the possible degree L monomials in the entries of X. So we can specify this polynomial AI, but by just giving the coordinates of each one of those monomials. And so that's what UI is. It's the list of all of those coordinates, so that UI dotted with X tensor L gives you fi of X. And then the matrix U just has rows UI for I equals 1 to M. And now that I have the polynomials, I can say what the relevant matrix is. I'll say that the ijth entry of M sub f is just the polynomial fi applied to the vector aj tilde. So you can think of the rows being indexed by the polynomials, and the columns are indexed by the vectors that you're applying those to. And our result says that this matrix has a large enough smallest singular value as long as the condition matrix, or the coefficient matrix, sorry, has enough large singular values. So that's what this last condition on U is. And to interpret this condition, you can think of it as saying how different your polynomials f1 to fm are. So if you have k plus delta n to the L large singular values, then your polynomials span that many dimensions. And you can see you need at least k because your matrix M has k columns. And so you need that many dimensions for the columns to span in order for it to be full rank. And it turns out you need a little bit extra, this delta n to the L, in order to, in some sense, make sure that the randomness in the aj tildes lines up with the large singular values. And we can show that this result is actually almost tight, and that any smaller power of n does not suffice. And the failure probability is also tight. OK, so our second setting starts out the same. We get these arbitrary input vectors, then we add a Gaussian perturbation. And now our matrix M has columns which are some arbitrary tensor products of those perturbed vectors. And now we can't hope that no matter which configuration of tensor products we choose, we get a good singular value bound. So you can see in this top picture, imagine you have a collection of vectors of columns of M where all but one of the tensor factors are the same. Then you're only left with n dimensions to work with. So you can only hope that M is full rank if you have fewer than order n vectors in this set. Or on the other hand, if they only overlap in one column, then you're left with n to the L minus 1 dimensions to work with. And so you might hope that you can allow up to n to the L minus 1 columns before you start running into problems. And our result says that this condition is actually sufficient up to some constant. So we might require a constant factor fewer overlaps than the maximum. But if this condition holds, then again, we get lower bounds on the smallest singular value. And by the kind of intuitive explanation I just gave, this condition has to be tight up to a constant. Now I'll give some applications of these results. The first one is to robust subspace recovery. So the setup is we get some subspace S within Rn, and S has dimension D. Then we get m points total, and an alpha fraction of them are going to be inlier, so they'll be within S, and the rest of them will be anywhere else in Rn. And then we'll perturb each of these with a random Gaussian perturbation again, The key, though, is that for all of the inliers, that Gaussian perturbation is only within our subspace S. So they're still in the subspace after the perturbation. And then we're trying to give a robust result. So an adversary can add an epsilon error to each of our points. And this error is not required to keep the points within the subspace S. And the result, and so our goal is, given these points that have gone through this whole process, we want to recover the subspace S up to some error. And our result says we can do this as long as the fraction of inliers that we get is at least d over n to the L for some constant L. And you can make this L as large as you want, and you just pay in the number of samples you need and maybe some constants. This is much better than you can do in the worst case. So in the worst case, Hart and Moitra showed that if your fraction of inliers is less than d over n, then this is NP-hard, assuming small set expansion hypothesis. Okay, our next application is to learning hidden Markov models. I'll give the setup for this. So you have a hidden Markov chain, which is Z1 to Z2 to Z3, and so on, within a state space of size R, and it's evolving according to a transition matrix P. And then you don't get to observe this Markov chain directly. Instead, you observe through this observation matrix A. And how that works is each column of A is, you can think of it as the mean of some sub-Gaussian distribution in Rn. And then when the Markov chain hits state I, you get a random sample from that sub-Gaussian distribution with mean AI. And the goal is to recover the Markov chain, so you want to recover the transition matrix P and the observation matrix A. Our result says that if you perturb the means of this observation matrix, then you can do this as long as the transition matrix P is sparse. And some things to notice, since you can make this L, this constant L as large as you want, you can deal with the case where the state space is much larger than the dimension of the observation space, which is known as the overcomplete setting. And some results in this overcomplete setting were known in the average case, but we believe this is the first smooth analysis result for learning overcomplete hidden Markov models. Our last application is to robust tensor decomposition. So the problem is the same as I've mentioned before. We're given a tensor. We want to find a minimum rank decomposition, except that our tensor now can come with some small error. And our result says that as long as the rank of the tensor is less than n to the L over 2, and if the error is small enough, then we can recover the decomposition. So this algorithm is based on a generalization of Cardoso's Fubbi algorithm, which stands for fourth order only blind identification. But the main point is that this gives us a slight improvement over previous smooth analysis results for the same problem. So before, I mentioned earlier that we can get a decomposition up to rank n to the L minus 1 over 2. Now we can go up to n to the L over 2. So for example, if you're decomposing sixth order tensors, you can get from, before we could only get a decomposition for rank n squared, now we can get up to rank n cubed. I'll give a very brief outline of kind of the main technical problems in the proof of Theorem 1. So to recall, you have this matrix with columns that are polynomials of your input vectors. And we want to bound the least singular value, which you can think of as roughly equal to this leave one out distance, which is just the minimum projection of any one column onto the span of the others. Now, skipping some details, it turns out that you can reduce this problem to showing that the projection of this symmetric tensor onto some subspace is large enough. There's a similar technical result in the original tensor decomposition paper, but instead of a symmetric tensor, you have this asymmetric tensor where each of the factors is perturbed independently. So somehow we have to reduce from the symmetric case to the asymmetric case. And that's what our decoupling lemma does. It looks complicated, but the thing to notice is that we're relating the probability that the projection of a symmetric tensor is small to the same probability for this asymmetric tensor, which we understand. And I think it's interesting to note that we're using this kind of decoupling, or desymmetrizing technique, to get anti-concentration results, whereas normally you'd think of it for getting concentration results. So I'll stop there. Thanks.
So do you have questions?
So when L was in the last slide, and then equals 2, you're matching what we know for matrices, namely the number of 2.
Sorry?
But when in the last slide, in the tensor decomposition, and you said you move it from into the limits 1 over 2, you enter the L over 2.
Right.
So that matches what we know for matrices, like that's consistent.
Yes, yeah. For matrices, it's actually easy because you can only have up to rank n matrices. Yeah.
There's another question? Yeah.
Are the results tied to Gaussian perturbation, or like anywhere like some small ball would be on the Perreault?
You mean the
Like general, like the proof itself, or like the results are really like playing everywhere perturbation?
I'm not exactly sure. I'd have to think about it, but we can talk about it more.
Okay, so thanks again.